Welcome back to ECE 220. We are now starting Chapter 6, and that means you're going to have several different things in your mind at once. We are 2 chapters ahead of where exam number 2 will be on Thursday. Thursday you will be tested on Chapter 4 material, which is consistent with homeworks 4, 5, and 6. Your homework, which is due Tuesday, is dealing with Chapter 5, op-amp material, and today we're talking about Chapter 6, which is inductors and capacitors. Mixed in with all of that, you still have to keep track of your labs. Group B, Section I, your lab is Tuesday of this week, and Group A, your lab number 2 report is due on Wednesday, and your pre-lab for lab number 3 is due on Saturday. Hopefully we're keeping track of everything. The main thing is in red. Your second exam is Thursday, and it will be covering Chapter 4 material, which you've now done the homeworks. Now you need to study, and if you want to look at practice exams, which I would recommend, look at some of those. Pretend you're a machine learning instrument, and now what do you typically do? You typically, to train, let's say, a neural network, you would give it many different examples to learn from, and then you would test it on something that it hasn't seen before. You might look at a few practice exams and then test yourself on one that you haven't seen before and see how you do. Just a strategy. Now, we will still be using Chapter 4 material throughout the course, so it is important to know MCA, mesh current analysis, and node voltage analysis. And when you're looking at circuits, you might want to just sort of step back and say which one seems to maybe be the most appropriate. Or if you just have a go-to, then just crank through. One might be more involved stepwise, but you should be able to get the same answer working it one way or the other. But one of those works all the time. Which one? Node voltage analysis can always be applied. Mesh current analysis works when your circuit would lie nicely on a plane where it doesn't have wires crossing over itself. If it's a planar circuit, then you can apply mesh current analysis. We will actually be doing that with new elements, new circuit elements, which in Chapter 6 involve inductance and capacitance, and correspondingly inductors and capacitors. So we'll talk about the symbol. Today we'll talk about inductors. We'll first show you the symbol, the circuit symbol, which is new, which in my drawing looks very similar to a resistor, but hopefully it has a little bit more curvature to it than the resistor. We'll look at the current voltage relationships of an inductor. They are now no longer static like Ohm's law. Now Ohm's law generalizes, and we have a differential relationship between current and voltage for an inductor. And why? Why? Because it actually stores energy. A resistor doesn't store anything. It just dissipates. An inductor has a magnetic field, and it will now store and release that energy in the magnetic field. We'll talk some inductor facts, and then we'll go through some examples and try to make the connection then with power and energy in an ideal inductor. I say ideal because you can now see we have a reality show at the bottom, and the ideal a little bit above that. Reality is you actually have some dissipation in that inductor. There is some resistance, but we will just assume that our inductors are ideal most of the time in this class. We'll have resistors to account for the dissipation of energy in our circuit. But we want to get comfortable with this new symbol, which has some curvature, coils. Think a coil. Now that's one way I might draw it on the left, or maybe I won't emphasize the coils quite as much, but you'll still see some loops or humps in the symbol. And notice that this orientation of voltage, polarity, and direction of current is consistent with the passive sign convention that we've been applying with resistors. We'll stick with that labeling and notation. If we have current flowing through an inductor from, let's say, left to right, then we will say the voltage dropped across that inductor is V sub L of t. And today I'm trying to emphasize the fact that we're talking about inductors, and so I'm going to subscript our currents and voltages with L, just to try to keep us comfortable with, oh, now we're talking about the voltage across an inductor. If you haven't seen an inductor, how many have seen something like this? And if you open anything up, a lot of times you'll see it, although now with surface mount technology, it might just look like a little block somewhere on your board that you're examining. But in general, you can see with an inductor this coil nature, and it's wrapped around something. And that is what we will then be using when we talk about inductors. You can sort of envision or think about these particular circuit elements versus what we've been talking about, which so far have been resistors and op-amps. So think wires and coils for an inductor. How does it work? Well, I'm assuming you've seen or had to create this iron filings with a bar magnet, this experiment, somewhere along your educational path. You've maybe seen these iron filings and how they orient themselves, how they align relative to a magnetic field. Well, the picture on the right shows the same kind of iron filings, but now, instead of a magnet, we have a magnetic field produced by current flowing in a wire. And you can see that this magnetic field is now a circular in nature, and it's a connected loop around, and it expands out from this wire. Now when you have current flowing, that now induces a magnetic field. Now we have a magnetic field, and depending on the direction, I see some right-hand rules going on here, depending on the direction of the current, and we typically think of current flowing, the positive charge is the direction that we associate with current. Then you can say, oh, I'm going to point my thumb in the direction, and now, okay, humor me with my drawing, but it took me 2 hours to try to draw that thumb sticking up with a hand showing the curls of your fingers. Those fingers now show you or indicate the field direction, the direction that the magnetic field is oriented relative to the current flowing through a wire. So this field line direction, what I'm trying to indicate here, is given by the finger direction. And if the current was flowing down instead of up, you can see now that your magnetic field lines are going in the opposite direction relative to the right-hand rule. What we will be interested in is the ability of these elements to store and release energy from this magnetic field, or relative to, or related to this magnetic field. And how that happens is actually through this differential relationship. Now, instead of Ohm's law being V is equal to Ri, we have V and I on the same consistent sides of the equality, but now we have a proportionality factor L, which is inductance, and the voltage now is proportional by L to the time rate of change of that current flowing through that inductor or that circuit element. We now need current to be varying with time in order to establish a voltage V in that inductor. So today, what you get to do is you get to combine your calculus, you get to combine your physics, and now we merge them all together. You have these magnetic fields, you have the description. Now we get to learn how to use those to analyze circuit behavior, and subsequently you would be able to use this to design something if you want to. But once we start getting these differential relationships, now when we start writing our KCL and KVL equations, we will have differential equations and not algebraic equations, which is why you studied the differential equations class. We now will start having to solve differential equations when we have inductors and capacitors in our circuit. Those now allow for energy storage, which give us this time rate of change behavior of current and voltage. You've taken multiple semesters of calculus. One of them, or maybe both of them, you worry about derivatives and integrals. You can now solve for the current from this differential relationship. But I'm going to start introducing some acronyms. I'm making a big deal about texting. This was created even before the cell phone, so Eli existed before the cell phone. We'll start connecting Eli with an inductor. That'll make sense in a minute. But we'll talk about Eli, the Iceman. Eli has an L in it for inductor. Ice has a C in it for capacitor. Ice may come tomorrow. But we have Eli today, and now if we simply try to solve for current in this relationship, now we can I now interchange the sides of these two expressions? I want to solve for current. I'm going to now put the right-hand side on the left of the equality and the left expression on the right-hand side, so that I now have 1 over L. Well, I just misspoke. I'll do that in a minute. Let me keep it the way it is. So now I have 1 over L, this integral from t0 to t, from some initial time t0 to the current time t, v sub L of a variable of integration, which I'm using tau, and now that's equal to this integral of di, which is I sub L of t minus I sub L of t sub 0. Now I can solve this for I sub L and see that I actually have two pieces to this. One piece of the current, or one component of the current, is due to the voltage from some time t0 up to the present, and another component is the initial current flowing, which we're labeling as I sub L of t sub 0. So this is now I sub L of t is now 1 over L integral from t0 to t V sub L of tau d tau plus I sub L of t sub 0. Where this now has two components, the current. This is the initial condition. We'll now be talking about what current was flowing initially when you start your analysis. Here's the initial condition, or the initial current at time t equal to t sub 0. And in fact, you could say, well, that was I sub L of t sub 0. That was from whenever, minus infinity, up to the present time of the voltage V sub L of tau d tau. That's the initial condition. That's one part of your current flowing through this inductor. The other component is, this is the current component due to the voltage from t sub 0 to the present. Wow. If the initial current flowing is 0, you wouldn't have that initial condition term. But if there is current flowing, then you have to say, okay, what was it initially? And then let me add to that this second component, or second part of the current flowing through this inductor, that is determined by the way the voltage has varied. We'll integrate that from t0 up to the present time t. What can we, oh, there we go. Now we find Eli. So where does Eli come from? E is supposed to be representing voltage, but traditionally, or maybe historically, where the E comes from is voltage may have been called this electromotive potential, E. But it makes for a nice acronym. We now have Eli. L is the inductance, and I is the current. And L is actually our proportionality constant. Why do you need to learn Eli or think about Eli? It now gives you the order, if you've forgotten how the current and voltage are related in an inductor. Now you can say Eli, and you can go, oh, the first letter, which is voltage, corresponds to what's on the left-hand side of the equality sign. Boom, there's E. The next two, L and I, L is going to be the proportionality constant. So the middle letter in Eli says, oh, I'm now going to have a proportionality of L, and I is actually differentiated. So this is now di sub L of t dt. If you want to have a way, a mnemonic way of trying to remember V is equal to L di dt, that's the differential relationship of current and voltage for an inductor, just remember Eli. And then you can write down V is equal to L di dt. Now I said the inductor allows us to store energy where? Where is the energy of an inductor stored? In the magnetic field. That's growing or collapsing. Growing and collapsing if we have a time-varying current. So we're storing energy in a magnetic field. And we have this magnetic field anytime we have current, anytime we have charge moving. It just has to be moving. It doesn't have to be accelerating. When we have acceleration, then we have electromagnetic radiation. But here we just have a magnetic field if it's moving. That's what we're concerned with now. From this representation, V is equal to L di dt, we want di dt to be bounded. We want it to be finite, obviously, if we want a finite voltage in our circuit. We don't want infinite voltages floating around. That means that we can't have the current changing instantaneously. Or this inductor resists abrupt changes in the variable that's differentiated, which is the current variable. So when you think of an inductor, you can think of, oh, the current is trying to continue to flow in that inductor. It's trying to resist abrupt changes in that current. Now, if you look at the current voltage relationship associated with an inductor, and now if you had I being a DC source, what can you tell me about the inductor now? The inductor acts like a blank to a DC source. What's the voltage across an inductor when you have constant current? Look at the Eli. And if you now have I being constant, what happens to when you differentiate a constant? 0. What's the voltage across an inductor when you have constant current? 0. What's that look like if you have a circuit element that has 0 voltage drop across it? What's another equivalent element that you could put in your breadboard to duplicate that? A short or a wire. An inductor acts like a short or a short circuit to a DC source. If you now have constant current, that coil now is like a wire. So if I give you a problem and it has a DC independent sources and it has a bunch of inductors in it, you can say, oh, I'm assuming now we're at steady state, or all the transients have died. So this has been in this condition a long time. Now you can just draw a wire across those inductors and you just have to solve your resistive circuit using Chapter 4 material, which you're studying for frantically to get ready for exam number 2, which is Thursday. Had to take a commercial break. Just like we have a resistor that has its units of ohms, now this proportionality constant, this L, this inductance, is measured in units of henries. That's named after a person. And it's given an H. Here's not a fill in the blank. This I'm just going to state. Inductance is really the term that we use to capture this property. Inductance is the property of this circuit element by which a time-varying current through that circuit element produces a voltage drop. That's what we mean by inductance. When we have a time-varying current, then if there's inductance in that circuit element, it's going to produce a voltage drop. That's inductance. In this class, maybe we won't be that practical. Who knows what our inductances might have, or these inductors might have in terms of their value, and we may start having 1 Henry. but in practice, you're usually going from pretty small, a microhenry, 10 to the minus 6, up to, well, I guess there's 10 henries, but in what you'll be building or would build, you'll be in the millihenries from 1 to 100, roughly. So from 0.001 henries to 0.1 henries, that's kind of some representative examples. But you could have a huge value of an inductance, which is 10 henries. Question? So now the question, I'm not quite sure I'm understanding the question, but we are going to be focusing on these inductors being ideal. So we won't really worry so much about their resistive properties. We'll just sort of assume they're small, or for the ideal case, we won't model the resistance property of an inductor. We'll just say it's all an inductor. So it's just going to have its inductance associated with it. We'll just say, oh, we have an inductor. Now we have L di dt for its voltage. That's what we will focus on now, is just the ideal scenario. Let's look at an example. Suppose we have a coil, an inductor, connected to an independent current source in a series loop. And now I'm going to provide to you the shape of the current. Now I'm going to say, okay, here's the current waveform, I of t, that I'm establishing with this independent voltage source. So now our voltage source is time varying, and in lab 2 you had a time varying source. It was sinusoidal. Now we have a sort of a pulse. It's kind of a weird pulse, but it has sort of a fin structure to it. We're going up, then we're constant, and then we're going down. That's the current that we're applying to this inductor. And we'll just assume that the time axis, that's what we're plotting current with respect to, as time. We'll just keep it as seconds, but a lot of times that might be shorter or have smaller units. It might be micro or milliseconds, so you need to make sure you're paying attention to the units on the horizontal axis. But for now, let's say here's our current waveform. Can you sketch the voltage waveform consistent with what you know to be true relative to an inductor and its current voltage relationship? And if you need some guide or some help, you could always just say, I'm going to call upon Eli. So now you have Eli, and you're going, well, that didn't help me a bit. But now you might remember that V sub L of t is L di sub L dt. If that's the case, now can you sketch what the voltage looks like? You need to find, is the current varying with time? Initially, before time 0, it is not. So we could say, well, the voltage looks like this up until t equals 0. Then what happens? Then we have a constant rate of change of the current, we have a di dt, a constant slope of rise over run, I sub 0 divided by t1. That's the slope, that's di dt, and we need to scale it by L. So in this case, we could say, oh, the voltage here is now L times I sub 0 over t sub 1. Since we're starting that slope at 0, we can say t1 minus 0, but I'm just going to collapse all of that into t sub 1. That's now the value of the voltage between 0 and t sub 1. What's the value of the voltage between t sub 1 and t sub 2? Current is not changing with time. It's now 0. It's now a short circuit. What happens next? Now we do have a slope. The rise is now minus I sub 0 over the run is now maybe smaller. It's t sub 3 minus t sub 2. And now we could say, oh, it's down here at proportionality, and it was a minus I sub 0 over t sub 3 minus t sub 2. In that first pulse of voltage, let's just put some numbers to it. For example, suppose we let the current be 0.1 amps or 100 milliamps. That's now what the value of I sub 0 is at its maximum. Then let's assume that T1 is now 1 microsecond and L is 100 millisecond. I'm sorry, L is 100 millihertz. L is 100 millihenries. Making sure everyone's awake. Someone is not. So we now have I sub 0, T1, and L. We can put all of those pieces together. L was 0.1, I sub 0 is 0.1, and T1 is 10 to the minus 6. It doesn't take much to create pretty large voltages. Now we have 10,000 volts. When we had 0.1 amps flowing at the maximum, but that did transition over a microsecond. So we built up to that quite quickly, and the inductor wasn't that big. It was 100 millihenries. Let's now continue with that idea. Let's look at this for some other waveforms. Suppose now I give you a current, case 1, where the current is as indicated, and we could say that that's a direct current. That's been true forever. That's what the dot dot dots mean on the left and right of that. What's V of t look like? It's pretty boring, isn't it? This is now 0, and the coil is a short. Case 2. What's V of t look like? I heard a constant. But now I have to be a little bit careful with where I start that constant, don't I? It's not constant before t equals 0. There is no current flowing, but as soon as we hit 0, then it jumps up. Well, that's supposed to be a flat line. Now we are constant, but we were 0 before that, so we actually have a step of voltage. We do have a transition from nothing to a value, a step of voltage. Which we really don't want to have if that was current. We wouldn't want to instantaneously change current. Then we would be saying, well, I'm getting ahead of myself. So let's look at the next case. How would we display the voltage, V of t? We would have a spike, wouldn't we? And mathematically, we represent these kinds of spikes as an impulse. And where would that impulse occur? Would it occur at 0? At 0, my current is nothing, isn't it? And it only transitions where? At t sub 0, wouldn't you expect the magic to happen where it transitioned? So we'll have an impulse of voltage at t sub 0, and then since the current is constant beyond that, we have 0 voltage. But where we experience the step in current, we would actually have Have you played with impulse, the Dirac delta function, in any of your classes? No? You will. So this now is an impulse. A is the area underneath that impulse. The impulse is a made-up, it's a mathematical function. It has no width and infinite height such that the area underneath that impulse is 1. So if we want the area under that impulse to be more than 1, we scale it by A. So A is the area underneath this infinitesimally narrow and infinitely tall pulse or waveform. And in this case, I'm just giving it an amplitude of A. This is now the Dirac delta function. Or it may just be referred to as an impulse. And the area, if you now integrated from 0 up to, let's say t sub 0 was 4. Let's say we integrated across that t0. We integrated from 2 to 6. Then the area underneath, just the impulse without any weighting, would be 1. The area under delta of t, and this delta of t does occur at the origin. So the impulse occurs when the argument is equal to 0. The argument of delta of t minus t sub 0 is equal to 0 for what value of time t? When is t minus t sub 0 equal to 0? When t minus t sub 0 is equal to 0, or when t is equal to t0. That's what tells you that that impulse is occurring at t sub 0. This impulse, delta of t, is occurring where? If you now had to sketch this one, what would it look like? Where would you locate the impulse? At -1? At -7? Where is the argument of that impulse? The argument is what's inside the parentheses. When is that argument equal to 0? It's at 0. So now the impulse delta of t is there. So this all sort of goes together. What if we look at another case? Now we have an exponential shape to the current, and then it flattens out to a constant value. What would the voltage look like of our inductor if we established that the current is looking like I of t in this figure? Would we have voltage? When would we have some non-zero voltage? Starting at t sub 0. So starting at t sub 0, we would have some non-zero voltage, and it's trying to go pretty big. What happens after a long time? What happens to our voltage? It goes to 0. So now we know that we have a peak, and then it does something like that. That's now more what, and it would probably be a little bit sharper than that, but you get the idea. I'm exaggerating the tail of that voltage. Now, these pictures taken together are supposed to give you some insight into the following question. Can I sub L of t change abruptly? Can it change instantaneously? Based on Eli, V is equal to L di dt. Can the current change instantaneously or abruptly? And here I'm going to have two answers. The first one's in practice. In reality, can the current change abruptly? That was sort of case 3, wasn't it? And we had to create a mathematical entity, a new waveform that was this impulse that had what? 0 width and infinite height, so that the area underneath that waveform, that impulse, was 1. That was a mathematical ideal waveform, wasn't it? In reality, does that exist? We like to cook things up mathematically to help us with our analysis, but in practice, can I sub L of t change abruptly? No. Why? Since this would require an infinite voltage. That's what Eli tells us. V sub L of t would be required to go to infinity. But we're not off the hook quite, because we want to play with these impulse waveforms from now until the rest of your career in electrical and computer engineering. So mathematically, we will allow those abrupt changes since we use delta of t, which we've now called the Dirac delta function, or the impulse, in subsequent classes. In our analysis, in our math analysis, in the second half of this book that you now have, ECE 320A, and a follow-on class on communications. How does your cell phone work? Well, more than that. But how do you now communicate? How do you transmit information? Having these waveforms available to us is important or nice. Now, in circuit models, if we had a switch in series with an inductor, that's not a good thing. We'll have arcing. We'll have things happening that we really don't want to have. We'll have high voltages present or created. So the circuit on the left is kind of the no-no. This is the no-no. And I've tried to now sketch a make before break type switch. So when you're switching on the right, now it will go from the left side to the right side, but you'll always keep the current flowing. That's a make before break type switch. On the left, as soon as you open that up, you've broken the connection, and the current wants to keep going, so it arcs across that switch. And that's not what we want. V of t would want to go to infinity, or we would have arcing. So here is what we're trying to avoid. Now, I probably may not be that diligent and keep these make before break switches. You'll just know that if there is a switch, then okay, hopefully he just forgot, and it will be nice in terms of allowing the current to flow continuously. So this make before break switch is supposed to allow the current to flow continuously. Now, we've talked about current and voltage, and the combination of those, if we multiply them together, gives us power. And power is related to energy. Now we can play with power and energy in an ideal inductor, and the energy is the magnetic field of this inductor. The inductor's magnetic field can expand and collapse, grow and reduce. If I now have this circuit element with voltage and current as labeled, what's the current voltage relationship on the right? What's the equation based on Eli? V, that's on the left, is equal to the proportionality constant, L in Eli, and then the last letter is what we differentiate. We now have that. If that's now our voltage, we now have a way of writing the power delivered to a coil. The power is just the product of the voltage and the current of that circuit element. The voltage is now L di sub L dt, and the current is I sub L. Once we have this expression for power, we can integrate that to find the energy. Power is the time rate of change of energy. Energy we can now find by integrating this power with respect to time. And now we can have this formula in our argument for the energy. Now we have this integral from minus infinity to t of L di sub L dt, I sub L, and now let me go, well, maybe change that to the variable of integration, d tau. we now have this integral. L is a constant. We're assuming it's not varying with time, so let's slide it out. But you could have a variable inductor. We won't. Let's just slide it out, side the integral. We now are integrating from minus infinity to t of I sub L of tau di sub L. What's the integral of x dx? That's what we have. We have the integral of I di. So now you're going, well, let me remember what this is. What is that? Isn't it 1/2 x squared? We can now use that to say, oh, the energy in our inductor is now L times 1/2 I sub L squared. And we're assuming that at minus infinity it was 0, the current. So now we know that the energy of our inductor is 1/2 L I sub L squared of t. And where is that energy stored? So now we have current flowing in this coil. If you want to know what the energy is in that coil, you just square that energy, divide it by 2, and multiply by the inductance. And that's now the energy in that magnetic field of the inductor. Oh my. Wake me up. We're out of time. You can now fill in the blanks here for these curves to relate current, voltage, power, and energy, and that's looked at in Chapter 6.